the topic what we will be discussing today is physics of rockets. Okay. So, then what exactly you mean by physics? Why not chemistry of rockets? Why you call the physics? Now, and one more thing I would like you to do, this is not only true for this lecture, but for subsequent lectures also. The moment you see a title, whether it is chemistry of rockets, physics of rocket, mathematics of rockets, there are certain questions or there are certain things which you expect to know after that lecture, right? The moment you see some title, you expect, see for example, the moment you see a board called a zoo, you expect to see certain animals, some lions, but suppose you see a zoo where only cats and dogs and some other animals are there, your expectations will fall flat. So, similarly, just in your mind, probably you can even write it down before every lecture, not only for this. The moment you see a title, just imagine what all the things what you want to know from this. Okay, at the end of the lecture, you can just have a mental comparison and something extra is required, you can just ask, just a suggestion. Okay. Now, we will go to the physics of rockets. Okay. So, what is this? This is a car, right? And what is next? Yeah. So, now we have rockets. So, what exactly all these three? On one side you have the automobile which you use on a day-to-day basis, then you have aircraft which of course you may use on a lesser frequency basis, and then you have launch vehicles. Okay, what is the fundamental difference between all those things? I am asking from a physical point of view. Okay, now since we are discussing physics, I am asking from a physical point of view or physics point of view, what is the difference between all those things? Yeah, exactly. He has answered it correctly because I asked what is the difference. But before even understanding the difference, there has to be some commonalities also, right? Basically, these are all modes of transportation. Modes of transportation, that is the first thing. That is another important characteristics of any scientist. In something what you see, in quite apparent diversity, you should be able to pick up some common thread. Then only you can make a law out of it, right? And Einstein and Newton, they all made laws just not by seeing how diverse things are, but what is the element of commonality. Based on that thread only they can form a law and all this. Okay, let us come back to that later. But what I am trying to say is first and foremost they are basically modes of transportation. They take people from one point to the other. Then what is the difference? As far as an automobile is concerned, it takes people from one point to the other. Aircraft does the other thing. Everything is same. There are differences. No, the distance will be different. But again I am concentrating on the basic technology. What is the difference in the technologies of a rocket, a launch vehicle and a car?
Propulsion engines.
Yeah, propulsion engine. You can have a jet engine in a car also. In fact, the fastest aircraft, automobile uses a jet engine.
Car travel in a road and aeroplane travel in air and the rocket travel in a space.
Very simple answer, right? But that is the crux of the problem. Because the moment you decide you are traveling on the land, you are making use of so many things which is granted to you by the natural laws. First and foremost, again, this seems very obvious. Why you are sitting on chairs? What will happen if I remove the chair suddenly? You will fall down, right? Why? Because unknowingly, you are all supported by the chair against gravity. Similarly, when you are on the surface of the earth is supporting you. The car is being supported by the earth. You don't have to worry. If there is no surface, car will fall till it reaches another surface, right? So, first and foremost, you don't have to support yourself when you are traveling through the road. You don't have to support yourself, number one. Number two, how to move forward. People have found ways long back. You have a wheel which can rotate, and when the wheel rotates, because of the friction between the wheel and the ground, you move forward. Only two conditions are required. The ground should be firm and it should offer the sufficient amount of friction or whatever you call, right? So, third question is propulsion. How you make it move forward, how you rotate the wheel. It all boils down to how you rotate the wheel. That answer is also found by people long back. You can use a bullock, you can use a horse, you can use any animal who is willing, who is ready to support us, not willingly ready to support us, we can make you to support us, fine. Even humans we are used for pulling, even today you use, right. So, mode of propulsion was that. But today again coming to automobile, it is not so, right. In automobile, we have a basic mechanism by which, now the next things are important, there is an engine. What does the engine do? The engine may take oxygen from the atmosphere. The engine has got, or the system has got its own fuel. It may be petrol, it may be kerosene, it may be anything similar to that. But for combustion of this fuel, you require oxygen. That oxygen, you just take it from the air. You just take in air, whatever oxygen is there in the air is sufficient. You burn it, you make the engine move, the rotary, the reciprocating movement of the engine will be converted into rotary movement of the wheel by various mechanisms, and because of that friction between the wheel and the ground, the aircraft will move forward. I mean, sorry, the car will move forward. This is the basic fundamental physics behind all those things. So it is true for a humble Maruti or the multi-billion Rolls-Royce. The principle is same. The only thing is the details are different. So this is the first point. Second point, again, you apply the same logic. An aircraft travels from one point to the other. Through which medium it travels? Air. Right, naturally. That's why it's called an aircraft. How all the questions are still the same. Right, questions are still the same. Who will support the aircraft? How you move forward? So who will support the aircraft? No, that is the detail. First, again, I may request you, there is a very simple answer first. What she told is exactly right. There is a pressure difference. They are the details, how exactly it works out. The fundamental, who supports it? Who supports it? Gravity tries to pull it down. Gravity will help you in certain things, but if you want to come down, gravity will help you. If you want to go up, gravity is against you. No, fine. It's an extension of what she told. Fundamentally, air is supporting us. Simple. Your first question should be very basic. Air is supporting you. Okay, the air is supporting you, or rather the aircraft. Fine, simple. So earth was supporting the car, now the air is supporting. Okay, can you catch this? If I throw it at you? Okay, it has fallen down, right? He was good enough to catch it, otherwise it would have fallen down. Why the air is not supporting this? Simple. If the air is so benevolent, friendly, omnipresent, omnipotent, why this has shown such a discrimination towards this particular remote control? Just because it is having the name Boeing or Airbus printed on that. Why the aircraft is supported by the air, but the same air does not support this? It should be same. The natural laws cannot be violated for this. The natural laws are same for this and that. Why it is not supporting?
The shape.
Now we will come to the details. Right. Now the question is not as simple as that of the wheel. You rotate the wheel, you move forward. But for an aircraft, you have to do something extra to make use of the benevolence of air. Right. Everyone will be helpful. Suppose I may be very benevolent, but unless someone comes and asks me the question in a particular way, I may not help you. Right. So it is how you have to make use of the air. Air is always ready to help. Air is ready to destroy you. Right. Air is ready to help you. It all depends on how you channelize the energy. The same electricity which powers this entire system can destruct entire buildings and all by a simple thunderbolt of lightning. So how to channelize it? That is a very, very important thing. So similarly, air, what we do, now you come to the details of you and you have mentioned. You have to make use of the air. First thing, again, two elements are there. Okay. Now first thing is, I will come to a little more physical explanation. Yeah. Now this is a typical aircraft. Can anyone recognize which aircraft it is? Sukhoi. It's one of the most common aircrafts. Okay, you will come to that later. So now, again, our topic, don't diverge, it is physics of systems, right? We will go to the rockets, but before that we will just go via aircraft and rockets. So anything, anywhere in the world, there will be mass, and if there is mass, there will be a mass-based attraction, which we call gravity in Earth, right? Everywhere you can call gravity for simplicity. Everything being attracted to something else by virtue of its mass is what you call gravity. So when you are talking about an aircraft, the aircraft will be tried to be pulled down towards the Earth by gravity. So that is there. So the first question is how to counter this gravity. Okay, so if the aircraft has, for a moment you just imagine the aircraft is stationary in the atmosphere, stationary, it doesn't move. Even then the question of avoiding falling down has to be addressed. Right. So something has to push it in the upward direction. So that is another fundamentals of physics. Everything works based on equilibrium. If something is stationary, it does not mean absence of forces. It basically means balance of forces. Clear? So if something is staying in air, the weight will always be there, and that will be supported by something else. That something else is what we call the lift. Conventionally we call it as the lift. This was found out by people long back. So there is a weight which is balanced by lift. Correct? So for lift, we depend on air. So this is the next logical point in our discussion. Now you forget the other part. Nobody will make an aircraft which stands there in air so that everyone can see there is an aircraft standing there comfortably. No. Aircraft has to move. So when an aircraft has to move, you have to give a force in this direction, which we call thrust, and there will be always be something opposing to the thrust, which will be air resistance, which we call drag. So these are the technical terms we should memorize and remember, not memorize. Memorize is a bad word, because it's something which against your will. You have to assimilate these based on this, right? So the 4 technical terms which we will be using throughout. There is something called weight, which is based on mass, which is always towards the center of the earth, and there will be a lift, which will be in the upward direction, and all these things, right? So now again I will be a little bit faster once we establish the fundamentals. Now how you will get lift? I told you, you have to have force in the upward direction, which you call lift, and air will be providing it, that also I have mentioned. Okay, but something you have to do to get lift, right? Something you have to do to get lift. That is 2 things. So if I may combine some of these points what you have mentioned, you have to channelize the air in such a way that there is a net upward lift. For that, you use something called wings. Okay, when you have a wing, what basically, I won't go into the details. When you have a wing, what will happen is that whatever you mentioned is a good explanation. There will be a pressure difference between the lower side of the wing and the upper side of the wing. As a net result, there will be an upward force. Okay, but suppose you have an aircraft on the launch pad, in the airport. You may be going to shower in an aircraft, right? So which is the aircraft which you are likely to go? It will be an Airbus A320. Okay, an Airbus A320 is having a typical wingspan of something like 56 meters or so. With that huge wing, the aircraft is standing on the runway. Why it doesn't go up? You have the wings. The fundamental condition I have satisfied, wings. No, wing is not sufficient. It is what you do with the air. I will give a simpler example. I am putting a paper here. Okay, paper will not float, paper will not fly. I can put a fan here. What will happen? The moment I put a fan here, you can see paper floating around. So what created the lift? Fan. Okay, because I switched. But what has fan done? It has created a velocity. It has created an airflow, not velocity. It has created an airflow over the wing. But can you put a fan on the aircraft, in front of the aircraft? No. Then the first cause principle will come. Then who will drive the fan? No. So what you do is you give. See, what you basically want is a velocity of air over the wing. That's what you want. So you remember Galileo, who first postulated the concept of relativity. If you want to have an airflow, just you are traveling in a bike, you can see the air facing your face. You can see the air blasting against you. There is no fan. You are moving. So if you want to have a relative velocity, if you want to have an airflow over the wing, you can move. Right? You can move and you can get the same velocity. So that's exactly what you do in an aircraft. Again, let me just put it like this. In this particular case, if the weight is more, the aircraft will fall down. If the lift is more, the aircraft will go up. If the thrust is more, the aircraft may forward. And the drag is more, it can even move backward. Okay. Now, these are the details. So this I would like you to just see, because since we are talking about physics. Now suppose you have an aircraft. I told you if you want to have the aircraft to develop lift, you should have velocity. Okay, so now you understood why the aircraft is rolling in the runway. Now when you are having a system, just imagine the aircraft is on the launch pad, in the runway, there will always be weight, the velocity is 0, and you should know that the lift, that the upward force is proportional to square of the velocity. So you can just see, now I am just starting the aircraft is moving down the runway, the velocity is going up, accordingly the lift is also going up. At one point, the lift will just balance the weight. Okay. Any addition of lift, what will happen? It will take off. It will take off because the net upward force is more than the weight. That exactly is what is happening. Okay, even though the aircraft may look very, very complicated, basic principle is this. Now, what the pilot does is, you will also experience, maybe after 20 minutes or 10-15 minutes into the flight, you will be climbing to some 10 kilometer altitude. You can note it. 10 kilometer altitude will climb, then the plane has to be horizontal, perfectly horizontal. So this is what we call cruising altitude. So at that point, the lift and weight will be same, and then the aircraft will come down. Okay, these details we won't go. Now our main business is launch vehicle. How these things work out in a launch vehicle? These things work out in a launch vehicle in a slightly different way. The thrust will always be there, the weight will always be there, right? But the drag is acting in the direction of weight, because when the rocket is going in the upward direction, the drag will try to pull it down. Something is absent here, no? What is that absent? Which is the lift is not there. Why lift is not there? We wanted lift, right? If you had lift, it would have been better. But as far as an aircraft is concerned, we are making use of the lift, we can make use of lift in a rocket. Possible, right? What is wrong in it? But only one problem is there. That problem is an aircraft is supposed to work only within the atmosphere. So we can depend on that lift. But a rocket has to work outside the atmosphere. So there is no air. So what's the point in having a wing? So and again, a rocket, how long it may travel? It may travel thousands and thousands of kilometers, right? Thousands of kilometers, now if not millions. Of that, how much is the altitude in which you can make use of air? Hardly 10 kilometers or 20 kilometers. The highest altitude an aircraft has flown was only 37 kilometers, a MiG-25 aircraft, only 37. So for 37, what's the point in having huge wings and all? It's highly inefficient. So you don't make use of lift. But if you don't make use of lift, who will do your job? Someone has to push it up, right? So that is where the difference of the aircraft. Now let me again ask you a question. Now I told you a rocket cannot function in, or rather our conventional mode of propulsion, what we discussed, cannot function in space. Why? Because there is nothing to support it, no air. You cannot take in air from outside and burn it. Still you have to use propulsion system. You cannot take air from outside and burn it, not possible. Then you don't have a medium to support you. So what you do for a rocket? One is simple, you carry both fuel and oxidizer. You carry both fuel and oxidizer so that you can burn it. That's simple. But what about the second thing? What is the mode of propulsion? You cannot use a rover, you cannot use a wheel, you cannot do something else. It's not possible, right? You cannot use something. Okay. So how do you do? How do you go? Thrust and all fine. It will produce thrust, but how it will go forward? So mode of propulsion system, whatever people knew till the last mid-19th century was not adequate. Okay, there is another example and parallel. See, when the First World War people were developing weapons, they found most of these cannons and all, no, they are unable to push it. Why? The road is very bad. Then someone had a brainwave. Why can't you make your own road? That is not like making a physical road. That is what you call which weapon? No. You have to make road. There is only one artillery vehicle which can travel anywhere irrespective of the road condition. Tanks. What does the tank do? Tank makes its own road. It takes the road wherever it goes, right? It has got what you call the treads. Similarly, what you do here is, people found out, there is a gentleman called this man, his name is Konstantin Eduardovich Tsiolkovsky, 1857 to 1935. What he has done, he was a Russian school teacher. He told, if you want to go out of Earth ever, it will be on the basis of reactive propulsion. Reactive propulsion. What is reactive propulsion? Reactive propulsion is very simple. You throw something, because of the reaction you go backward. Simple, right? I have thrown you this remote. I would have gone, a force would have acted upon me in the backward direction, but I am strong enough, and this friction between myself and this earth is good enough to resist that. So whenever there is a force in one direction, there will be a force in the opposite direction. You can make use of that. You can move forward. So if you are throwing something in this backward direction, so I will show one or two simple experiments. What's the time now? 11:15. Okay. So it's a very, very basic thing, but it's very instructive. Now there is a balloon. Balloon is filled with air. Okay, very simple. If you remove this your hand from here, what will happen? The balloon will go, right? And then why the balloon moves? Action reaction, right? Because whatever air is coming out of it is creating a reaction, etc., etc. That is well known. Now here I want to take a small deviation, because you're all 9th standard students. You cannot be fooled by such gimmicks like showing a balloon working, etc. You want something more, right? So I will show you one gentleman here. Who is this? This is Sir Isaac Newton, 1642 to 1727, long back. Now Einstein was a very serious man, was a very morose man, but when he sees children like you, he may smile. Generally he is a very, very serious man. He rarely used to even talk. But what has Newton done? Newton has formulated the fundamental laws of physics. You can interpret it in different way. I won't go into the detail. I will only say the fundamentals, namely a body remains in the state of rest or uniform motion unless and until external force is applied. When a fellow is traveling like this, okay, and suddenly when the train brakes, what will happen? He will move forward. You see the box here, it moves forward, right? Because the force is acting on the box, even though the aircraft or the train are stopped, the force is still acting, the inertia, because of its tendency to move forward. So this is what Newton has said in the first law, but you are more interested in the second law. Many people say the rocket basically works on the third law of Newton, or rather it's a wrong way to say that. Even if there was no Newton, people have made rockets, and that's a different, but still the Newton has identified this particular natural phenomena into a law which we call Newton law, right? Okay, so now what has Newton mentioned in the second law of motion? This is very interesting, and you please note it very carefully. When a body is acted upon by a force, that, okay, in other words, the rate of change of momentum of a body is directly proportional to the force. That's what he told in plain English. Okay. Now what does it say? Now you watch it very carefully. What is momentum? Mass into velocity. Okay, you should understand Newton has put in 1684 where the concept of energy was not there. Energy was put subsequently by Gottfried Wilhelm Leibniz. Okay, so Newton has put theories like momentum. Newton has given a lot of importance to momentum. If Newton had lived today, he would not even use the word momentum. He would have directly gone to force and energy and all. Now what is momentum? Mass into velocity. Now what did Newton say? He said the rate of change of momentum is equal to force, right? What is rate of change of momentum?
Mass into velocity by time.
Yeah, or momentum by time, which is nothing but mass into velocity by change. Okay. Now just see I am just doing a simple manipulation. You just see the equation. I am just moving the time only to velocity, acceptable as per the established rules of mathematics. So what is velocity by time? Acceleration. Very good. So force is equal to mass into acceleration. This everyone knows. Now from the rocket point of view, I am just trying to tweak it a little bit. Again, very fundamental. Rate of change of momentum, again mass into velocity. Clear? Now I will move the time towards the left. Rate of change of momentum is also equal to mass divided by time into velocity. I am keeping the velocity as it is, but I am using the time only to divide the mass. Now what I will get? Force is equal to mass divided by time is called the mass flow rate. Okay, this is very, very important. This element many people miss when they try to understand rocketry, right? They know that rocketry works on the third law of motion, but unless you are clear about the second law, they will never understand. They will parrot the statement like for every action there is an equal and opposite reaction. But here it's very important. The force is equal to the mass flow rate into velocity. That is F is equal to m dot into v. So you just see this. You could understand, no? The rate of change of momentum, you can explain it like this. So force is equal to m dot into v, and the force is also equal to mass into acceleration. This is the fundamentals of rocket. This is the fundamental equation of physics as we apply for fundamental rocket movement. Now I will just explain the word mass flow rate. What exactly mean by mass flow rate? The moment I ask you, can you make force without acceleration? You will say no. Why? Because Newton has said that force is equal to mass into acceleration. I am saying it is possible. How? You can have something moving at constant velocity, but you should have a lot of mass flowing at a particular time. A mass cannot be stationary. So when you throw out mass at a larger rate, even if the mass is traveling at the constant velocity, you can still get force, and that force can be applied somewhere and you can move up. So this is something which you should remember, right? This you may not find in any other common explanation of Newton's law. They will always say this, that and all. Now the third law is fairly simple. Okay, so here also the point is same. Whatever I have mentioned is equally important. For every action there is an equal and opposite reaction. For every action there is a equal and opposite reaction. Okay, we would have done some small demo with this chair itself, but because of lack of time I won't do that. Suppose I am pushing against this wall myself. Will I move? But as per the Newton's law, I am acted upon by the same force, right? I am applying a force on the wall is applying a force in the opposite direction, but these forces are same. But suppose I am sitting on this particular rolling chair and I apply the force, what I will do? I will move in this direction, right? So my movement will be equal to the force exerted on the other side. So we will leave this at this particular point. So now the fundamentals of this is clear to you? Very good. Now again we will come back to the experiment. Now you understood, now you are seeing the balloon in a different perspective, right? Why? Because from the balloon no acceleration comes out. From the balloon only mass flow rate comes out. From the balloon only air particles at a particular velocity comes out. Because of that there is a force, right, which is given by m dot into v. Now because of that force, the force is acting upon the balloon, balloon has got a fixed mass. It is not mass flow. So that balloon will accelerate an acceleration of A. So both m dot A and m dot V into m into A is getting equated at this point. So the acceleration of the balloon here will be m into A, and whatever force which is creating the acceleration will be, yeah, very good. Now another example. Now you take a typical, what is this? This is a cannon. Okay, so I am firing a cannon. What will happen when the projectile is moving in the one direction? Okay, the cannon will move in the opposite direction. This is an actual experiment what people have done. See the cannon moving the opposite direction?
Yes.
Yeah. And you have seen some stoppers deliberately kept, otherwise this cannon will move. So that begs the question, why can't we make a vehicle with cannons, series of cannons, right? So you stand on the backside with a cannon, keep on firing, the vehicle will move forward. It will move forward? It will move forward. But you will have a trail of tragedy on the, I want to use the word dead body and all. This is not practical. What I mean is not practical. Even though it makes use of the same physical principle, it's not practical. So what we use is, instead of cannonballs, we use small quantities of air, like in the case of balloon. But again the next question, why we are not going to space in a balloon? There is a very famous book by Jules Verne written in around 1867. What is that book? Anyone someone is interested in reading, you know?
What's that?
There is a famous book by Jules Verne. Huh? Around the World in 80 Days is one book, but with respect to our topic, he has written 2 more relevant books. Okay, we'll come back to that if then there's time. Now my point here was, you cannot go to space in a balloon because the amount of energy what the balloon gives is very small, because the energy of the air which is coming out is very feeble. You can imagine, right? Can you ever imagine yourself traveling into the moon in a balloon? Why? Because intuitively you know that the force is less. Even though you don't know what is the amount of force, intuitively no, it's not there. But when someone says you can go to moon in an aircraft, sometimes you may believe, because aircraft you know is powerful. Fine. Now the next question is, we are going to another experiment which is more powerful. This is a very, very old experiment. So there is a water in this particular jug. When you heat it, when you burn it, the water is converted into steam, and the steam comes out through 2 jets and it rotates. Okay. So here what is the difference between the previous case and this case? The previous case or this, which is more powerful? This is more powerful. Why this is more powerful? Because the velocity of the jet which is coming out is more. Okay, so m dot is there, v is more, so this will be more. So what is the message from this? If you want to have a more powerful rocket, you cannot just throw out air, cold air like in the case of a balloon, but you have to throw out extremely high energy particles out of it. It should be having 2 things. One is high pressure, high velocity, high temperature and high velocity. These 2 should be there. So this was found out quite accidentally by someone in China, possibly in the 10th century or so. This is what you call a rocket. Here what you do is, first time they have found, when you have a mixture of potassium nitrate, carbon and sulfur, okay, it has got all the ingredients, it has got the fuel, it has got the oxidizer. When it chemically reacts, it gives out large quantities of heat, high velocity gases, and then because of that what will happen? Because of that, when you lit it, it will go forward. So this is the first, you can say, modern rocket. Here you understood, no? It throws out mass at tremendous velocity. Because of the reaction, it goes. So this is the direction of the jet and this is the direction of the rocket. So now with this, we have just come to the fundamental aspects of rocketry. It's as simple as this. The moment you see a rocket, see the power of the greatest minds are, they are able to see simple principles behind a very, very complicated things. Right? This is very, very important. So this is the hallmark of great scientists like Einstein, Newton, etc., etc. They have seen the simplicity behind these complicated things. Whereas we are sometimes trained to see the opposite. The moment you see something, immediately, oh, how complicated it is. See the wheels, see all these kind of things. It's not so. Fundamentally, you have to see that, see, I remember a case when I was in my school days, like, I used to see the railway station, I used to be in the railway station and I used to see the diesel locomotive. And diesel locomotive is a very, very complicated thing. And never we can understand this, how complicated this is. Then I thought, George Stephenson some 120 years back designed the same thing as it is. So I thought, how complicated this system is, how such a complicated system he has developed. But if you see the original system which our George Stephenson has derived or made, it's very simple. Okay, but an expert will see even within a complicated system, the basic things. And an engineer or a physicist or a scientist will see it better because he knows for what purpose each and everything is there, right? So that is very important. So my advice to you would be, or suggestion to you would be, see things in its elements when you look at something. When you go to SHAR and see systems, you keep this in mind. Now, this is what I was trying to say with respect to the rocket. I won't go into these details because it's not exactly in our topic. But here, this is how a aircraft engine works. This is important to understand when we discuss about rocket engines. So here in an engine, the same type of engines you will be using when you travel to SHAR. Okay, so here there will be an engine like this. So what they do is, okay, I won't make it very complicated. The air will be taken from outside, then fuel will be injected here, it will be burning here, and because of that a jet will be produced, and because of the jet you will get velocity, and because of that you will move. This is what you call a turbofan engine. We won't go into the details, but the point what you should understand is, here also a jet is thrown out. Because of the reaction of the jet, the plane moves forward, right? And the burning is taking place. Here again one more point what you have to understand is, you have to take air from outside, oxidizer from inside. Now I will put another point also. It's an actual experiment done. Okay. So okay, this is a movie based on our Tsiolkovsky, the same man. But see, now the question was, in the last century people are worried how to go to space. If you want to go to stars, what is the mode of propulsion? So what he told is reactive propulsion. You throw out something from the rocket using a chemical system. Because of the reaction you will move forward. This is what people told, but many refused to believe, because they all believed the theory of the boat. You row a boat because you are pushing the water backward. Because of the reaction of the water you are moving forward. This is what people had in their minds. So they said it's impossible to move forward by throwing something alone. Understood? No, we also sometimes feel like that. Unless there is something against which we can push, it may not move forward. So this is a simple demonstration which Tsiolkovsky has given. This is actually a movie. Now what he is doing is, just see this. This is not a camera trick or anything. It's an actual experiment. So this gentleman who is acting as Tsiolkovsky, he is throwing the oar or a wooden plank from the boat. What we should see? If the Newton is right, Newton of course is right, he is proved right, the boat should move in the opposite direction, right? But when we ask this question to people generally without explaining the way, they all say the boat will remain stationary, because they have never seen in a day-to-day life now people throwing out something and the boat is moving forward. Now you see this. Now see, he is throwing. Yeah, he is not stopping, he is throwing something else also. Now he has thrown so many other things. Yeah. See, last even the bucket adds to the velocity. See now he is asking, now you understood. See, the point is, as boat which is completely stationary, by throwing something out, this is gain velocity. So this is the exact principles of rocket. Two things are important. You have to throw something out, you have to reduce your own mass. So this is the fundamental principles of rocketry. So how much time I have? Oh, okay, very good. Now the other question is, 2 or 3 things I will just try to mention. Now I told you very clearly, if a rocket has to develop thrust, what exactly you want, you only go to the equation, don't worry about the complicated rockets. You just think about the basic equation of rocket, m dot into v, right? M dot into v. So 2 things are required. One is large quantity of gas or mass you have to throw out. Second thing is it should have velocity. So you should have maximum velocity, right? So how to generate maximum velocity? Generally, forget about rocket engine, don't even think about rocket engine. How you generally generate velocity? You can use fan, no? Burning will not generate. You can use a fan. Fan will give velocity. You can use a pump to some extent, you can use velocity. But these are all not practical. So the question is, how to get velocity? Velocity is what you want, not temperature, not pressure. Now the question is, every reaction process, every chemical reaction process will produce lot of pressure. That is known, right? Classic example is, the automobile engines. When a chemical reaction takes place, the total volume of the reaction products are very large compared to the reactants. So the pressure will be high. You understood, right? So when you burn something, suppose if I burn as 1 gram of say gunpowder here, it will produce thousands of cc's of carbon dioxide and potassium, all this kind of hydrochloric acid, HCl, everything will be produced. So the volume is quite large. So when the volume becomes so large, what will happen? The pressure will be higher. So that's how when you have an explosion and all, no, the pressure wave is destructing the buildings. So it's very, very easy to get pressure. The moral of my story is it's very easy to get pressure and temperature, but it's very, very difficult to get velocity. Okay, so what you do? You go by the easier path. You try to first get pressure, then try to see that pressure can be converted into velocity. That's what we do. This is another important thing about physics. If you don't get it directly, you get it indirectly. Right? Suppose I want to have, suppose we are in a country where we don't have any currency system. I want a computer. Okay, but you want, you will give me a computer, but you don't want a chair which I have to barter with you. Okay, I have a chair for which I can barter a computer. She is having a computer, but she is not ready to give me because she don't want a chair. But I can always find a third person who is ready to accept the chair and give me maybe a projector which she may like. So this is how we do in physics. Okay, we always use an intermediary mode of energy exchange, and this is again all in conformation with the law of conservation of energy. This is again something we should very clearly understood. The physics works with all laws subject to the constraints put by conservation laws. What are the conservation laws? Law of conservation of mass, law of conservation of energy, law of conservation of momentum, and if you go further up, we will study there are law of conservation of species and something else. Okay, so you can make anything subject, just like for example, in any country, a parliament can make any laws which is within the constraints set by the constitution. Okay, who will check whether it is within the constitution? The court will check. So judiciary. But here in physics, you cannot go to a separate judiciary. The nature will take care of itself. The judiciary is inbuilt into the natural law. So you cannot make an equipment which will violate the laws of physics and work. Right. So what I am trying to say is you can always make use of the natural laws to do that. So there is a simple principle involved. The detailed engineering of that we don't have to worry. That is what you call nozzle. Okay. So this nozzle is called Delaval nozzle. Delaval is a place in France where there was a person called Delaval. He was in dairy business. So he accidentally found, see, in the tube, rubber tube through which the steam he was using to have pasteurization of the milk, when he is pressing the tube, the velocity goes up further. Simple principle, right? So this is again, if you know the Bernoulli's laws and all, you can easily explain this. So the principle of a nozzle is something like this. You can burn something here in the nozzle. That is the combustion of the rocket, what we are saying. What you will get? You will get very high pressure, but zero velocity. But what you want? You want velocity. So the moment you provide a system like this is what you call a convergent divergent nozzle. Okay, this is the combustion chamber, this is the convergent portion, this is the divergent portion, and this region is called the throat, constriction. Okay, so when you have a system like this, the detail of mathematics we don't have to worry. What we will see that the high pressure is automatically converted into velocity. You don't have to use any fan. The moment you give pressure and you give a shape like this, the pressure is converted into velocity. You see the graph, a very simple graph. As it goes down the axis, the pressure falls and the velocity increases. And you will be surprised to know what is the values you get. In a typical rocket engine, the velocity of gas here will be 0. Can you guess what is the velocity here? Any guess? Any number? You may be right, or sometimes you may be up, you may be on the right track. Around 1000. Unit is another thing. Always say the unit. 1 kilometer per second, right? So the moment I say 1 second, you are traveling 1 kilometer. Can it be that fast? Can it be that fast? No, because you should remember, I am not using anything else. 8 kilometers is the speed of the rocket. I am not using anything else. I am only burning something like a cryogenic fuel, and I am only using a shape, nothing else. What is the velocity I will get here? He said a good number, 1000 kilometers per second. Sorry, 1000 meters per second. In 1 second, that means the gas which is coming out after 1 second will be 1 kilometer away. That is the kind of velocity at the exit. Is it more or less? It's more, no? That is where the difference comes. Actually, it is less by a factor of 4. In a typical cryogenic engine, you will get the velocity something like 4.5 kilometers per second at the exit. Okay, in a solid water, you may get something like 2.5 kilometers. Now you understood what is the power of a nozzle. a pressure of the order of 50-60 bar pressure, that is 50-60 times of the atmosphere, is converted into velocity of the order of kilometers per second by simply using a shape, nothing else, right. So now we have got all the elements of a rocket. We got the fundamental laws, okay, we got the basics of principles to convert velocity, we understood the source of energy. What is the source of energy? A chemical combination of a fuel and oxygen. We got everything. Now what is next? Now you may again imagine, think, Newton had all these laws in 1684, right. Why haven't we made a rocket till 20th century? That is where the technology comes in. Science is different, technology is different. It's only technology which makes things, science gives the fundamental principles. So technology of making this were not available. It requires a very, so if someone told, someone is interested in cosmos, who told, favorite book is Cosmos? You told, Carl Sagan's Cosmos. Okay, so there are a lot of, in some of these chapters of Carl Sagan's Cosmos, he mentioned about the technology in the shores of the cosmic ocean is the first chapter. So from that point, he takes us to the development of technology. You had science in the beginning. Even since the day the human being or the human race has evolved, there is science, because whatever you try to understand is science. Okay, but technology also will be evolving, and technology is the one which makes science into practice. So what I am trying to say, these are all fundamental scientific principles. This anyone in the world will know, provided they can, but nobody is converting into a technology. That's where the difference is. So the technology is to make such thing works. Now you understood, no? We have a very basic element. Yeah, please.
So pressure is directly proportional to velocity?
No, I did not say that. Pressure is not directly proportional to velocity. What I am saying is, in such a system, pressure is converted to velocity, not linearly. Okay, so the reduction of pressure will be equivalent, not equal to the increase in the velocity. Why I say it, everything depends on the change of area. There are so many other parameters which are there. Now we understood the fundamental principles of rocketry. So now one or two other points and we are practically done with the basic part. Now how to make a rocket? We understood we had to make large mass flow rate. We already have the nozzle. So how to generate large mass flow rate? I again told you, you have to have a fuel and oxidizer. That is what we call chemical propulsion. So there are so many fuels and oxidizers. The classic fuel and oxidizer is what? The normal wooden material. You can have dry leaves. These are all basically fuel. Who will be the oxidizer? Air. But those things are not efficient. They cannot make a rocket work. So what we do is we make a very complicated set of chemicals as rocket fuels. Okay, but here as far as a rocket is concerned, you have to always say the fuel and oxidizer. Whereas in the case of an automobile, have you ever said, no, you go to a petrol pump and said, I want a propellant combination of petrol and air? You don't have to say that, because air is available. You don't have to tell. If you tell, he will be confused. He will be worrying, what exactly, you understood. So what we have to have is, as far as a rocket engine is concerned, you have to always have to mention what is the fuel and oxidizer. So rather than saying fuel and oxidizer, you always use the common word called propellant. So as far as rocket is concerned, use the word propellant, which includes fuel and oxidizer. Understood? Right. Now, what are the fuel and oxidizers you can have? You always would like to have the most energetic ones, naturally. Okay. But sometimes the most energetic one may not be the most feasible one. So what you do is, so now depending upon the physical state of the propellants, you can have solid propulsion system, which basically means the fuel and oxidizers are in the solid physical state. That's all. Okay. But there is a problem. A solid system, the fuel and oxidizer will not, you have learned the fundamentals of chemistry, something like Le Chatelier's principle of chemistry, etc. Reaction, you have studied Le Chatelier principle. How does the chemical reaction take place when there is a molecular collision? That you have studied. And the chemical reaction will be better if the surface area is larger. That also you have studied. A chemical reaction will take place with more surface area. Better the surface area, better will be the reaction. So you have to, if in a solid state, if the reaction has to take place, it has to be powdered. Okay, it has to be powdered and it has to be mixed together. The fuel and oxidizer has to be mixed together. So when you mix the fuel and oxidizer, it will fall down. It won't remain in the mixed conditions. For that you use what you call a binder. So there will be a chemical called a binder which will be keeping the fuel and oxidizer in close proximity. When the fuel want to react, there has to be an oxidizer. Oxidizer cannot be in the next district, right? So a matrix will keep these together. So that is how you define a solid propulsion system. A solid propulsion system will have a fuel, an oxidizer and a binder. This and all you may not have to remember. So this is how a solid propulsion system works. But here again, you just see this next graphic very carefully. So what you do is, this entire system is filled with propellant. This entire system is filled with propellant. So what is the most prominent part you noticed here? Nozzle. Now you can very clearly understand, why all these things are there. So when the reaction starts, see, the entire rocket will burn as a single stack, and then this high pressure will be coming, high pressure gases will be coming out. Here it will be converted into, gradually converted into velocity, and then the rocket will move upward. So this is what a solid propulsion system is all about. So now you understood what is a solid propulsion system. But solid propulsion system has got lot of limitations. First of all, beginning itself I told you should have a very powerful system. Solid propulsion system is very practical, very useful. There are a lot of advantages, but it is not very efficient. It's very powerful also, but like many people who are very powerful, sometimes they may not be as efficient. Similarly, vice versa, and there are some people who are both powerful and efficient. So like that, we want to have a powerful and efficient combination. So solid propulsion does not fit the bill, but it has got lot of applications, so we still use solid propulsion system. Now the next is liquid propulsion system. As the name suggests, the fuel and oxidizer will be in the liquid condition. The fuel and oxidizer will be in the liquid condition. I hope there is a class on chemistry of rockets. Is it so? In your subject there is no chemistry of rockets? Somewhere down the line, lectures? No. Fine. There, Satyaja? There is one on propulsion. Fine. So that will be, we'll discuss that at that particular point of time. So here what I am only trying to say is, I won't go into the details, that the fuel and oxidizer will be kept in different tanks. Not mixed like this, it will be kept in different tanks. There will be a fuel tank, there will be an oxidizer tank, and then fuel and oxidizer has to come to the engine, no? The fuel and oxidizer has to come to the engine, and the fuel and oxidizer comes to, so these are all engine firing. So fuel and oxidizer has to come to the engine, and then it will create a jet, and using the same principle whatever we have mentioned, it will move out and you will get energy. One big advantage of this system is, you can stop when you want and you can again restart, because you just like what you close the flow in a pipe, you just close it, you again restart it. So this system is much more versatile. So whenever you want to have very complicated missions like Mars mission, Chandrayaan and similar complicated missions, we always go for liquid engines because it can be stopped and again restarted. So now I will have only a couple of points to add. Now again, you may, since we have come to this level, we will also make a brief idea about the cryogenic engine and go to the last part. Okay. So what exactly is a cryogenic engine? You have all heard about cryogenic engine, right?
Yes, sir. The materials have a very low, are present at very low temperatures, and they have very low boiling point.
Yeah. What exactly is cryogenic temperature? Whatever you said, second is the right one. In
minus 270, absolute zero. Extreme, it's extremely cold.
Yeah, it's extremely cold. Yeah. What is extremely cold?
Below 0 degrees.
Yeah. Another important point. See, when I say extremely cold, right, what kind of statement is it generally? It's a subjective statement, right? Suppose if I ask a friend from Siberia, now this may be extremely cold for us, but he lives in a temperature minus 50 degrees Celsius on a day-to-day basis. For him it's not extremely cold, right? Similarly, a person living a Bedouin tribe living in the African desert, for him 50 degrees Celsius is every cakewalk, right? Whereas for us, anything above 30 we will feel frustrated. So what I am trying to say is, in physics again, never use the word like extremely high, extremely low. You always have to do with a number. In normal conversation, fine, extremely, we know, because for us, the extremely high, cold, everything will be same. But in physics, you always have to use proper numbers. So for cryogenic engine or cryogenic technology, what you said is correct. The moment you go to low temperature, it is called cryogenic. So the next question you should have, what low temperature? What is the value?
Minus 250 degrees.
Minus 150.
Yeah. The general convention is anything below minus 150 degrees Celsius, unit again is important, is called a cryogenic range. Okay. What he was referring to was the temperature of hydrogen. Liquid hydrogen is minus 253. But anything below minus 150 degrees Celsius is called a cryogenic range. This is nothing to do with cryogenic engine. This is only a term what we use. Okay. Anything below minus 150 degrees Celsius is cryogenic temperature range. And some fluids which is having its melting point below that range are called cryogenic fluid. That's all. The word cryogenic has got nothing to do with rocket or anything. It's only a generic term. Okay. Now, just see this. There are different rocket engines what we use. Okay. Some are solid propulsion system, some are liquid propulsion system, some are semi-cryogenic, etc., etc. And in rockets, there is something called a specific impulse. Don't have to worry about it now. This is what you call specific impulse. This is something like the mileage of a rocket, how efficient the rocket is. Suppose if you see the other system like solid, the numbers is in this range. Now when you come to a cryogenic engine, just see this slide carefully, it's much higher. So a cryogenic engine is having or rather I won't say cryogenic, I won't say hydrogen oxygen engine is having very high performance index. It gives you very good velocity. For the same quantity, it will burn for much longer duration, right? So naturally we want to have it, right? Oxygen and hydrogen we want to have it, but there is a problem. The problem is the density of hydrogen is very small. Suppose if I take an example of a suppose if I use in the GSLV system, the last stage, okay, I don't have time, but still I will just tell you. So in the cryo stage of GSL, we use around 2000 kg of liquid hydrogen. So if we use hydrogen, what is the size of the tank? The size of the tank will be around 3 kilometers. Size of the tank will be. So what I am trying to say is hydrogen is the best fuel, but if you use hydrogen in an engine, the tank size will be 3 kilometers. 3 kilometers tank. It's farthest higher than even the Burj Khalifa or the highest building. It's not possible, right? Then why you want to go to orbit? You can climb to orbit if there is a stage like this, right? So it's impractical to use hydrogen, even though hydrogen is the most efficient. But one simple thing, how to reduce volume? Two things only are possible to reduce volume. One is pressurize it, second one is reduce the temperature. So we will reduce the temperature, good. So but reducing temperature, I am trying to reduce the temperature here. At 0 degree, what will happen? Water will freeze, and then at minus 150, the cryogenic temperature range has started, but there is no sign of hydrogen going to liquid. Okay, at around minus 193, oxygen will liquefy. So at least that much part is solved. But again, when you go down at minus 253 degrees Celsius, that is almost as close to absolute zero, hydrogen will liquefy. So what is the problem? The problem is if you want to use a cryogenic engine, you should have a system where the temperature is at minus 253. Minus 253, unimaginably low temperature. LOX equally dangerous. But the biggest problem is in the engine, temperature is 3000 degrees Celsius. So that combination and the difference between all these things are a few centimeters. At one point you should have 3000 degrees Celsius, on the other point you should have minus 250, you have to have insulation and all. So this was a very big challenge, and like you would have noticed, most of the material cannot be used at this condition. So this achievement India have done in 2014 with the GSLE 15. So this is one point with respect to this, right? So the last couple of points I would just want to see, and we'll wind up. Yeah, so like that now we have a lot of engines and other kind of systems. There are a lot of controls, systems, etc. Okay, there are various launch vehicles. We won't go into the details and all. And the next session, Dr. Shanid will talk to you about the physics of satellites, which is completely different. Fundamental laws are same, but the applicable things are. So now I will go to my last point. Yeah. Yeah. Now I will take our PSLV as an example and explain to you how a typical mission, that is again coming under the purview of physics. So I have told you the rockets are primarily system which produces high temperature, high pressure or high velocity mass, right? For that you have a nozzle, okay, and then depending upon the type of propellants you can have different types of categorization like liquid, solid, etc. Okay, and what does it do? It gives an acceleration, right? M dot V gives M dot A. So it will give acceleration to a launch vehicle. It will keep on accelerating the launch vehicle till it reaches space or wherever it is. And space, what do you mean by space? Again, another question.
100 kilometers to
Yeah. Above, again, now you understood, no? So if someone says it's very high, you won't be satisfied. You should not be satisfied. You have to ask how much. Tell me, I want a number. Okay. So he will say some number. Then you should ask what is the rationale for this number. I can say some number, no? Carmen has given 100 kilometers. I can give some other number. Like, what's your name? Sridev. Sridev can give a number. Sridev number, 92.3 kilometers. Nobody will question him. But there should be a rationale behind that number. Otherwise, nobody will follow. Right? You can edit his own Wikipedia page and say that Sridev number is defined as 93.2 kilometers. What is the reason? No reason. That's not physics, right? So there should be a rationale. Carmen line has also got a rationale, which we will discuss if there is time. My point is PSLV is a launch vehicle which does what? I will just see. See, PSLV is a launch vehicle and this is what? This is what? Nozzle. How big will be a nozzle? Because I have told you, know, the nozzle, the principle. How big should be a nozzle? Will be this much, this much. So if I place a person, an average sized person, this will be his size. So PSLV, when you go to SHAR, you will see the launch pad of PSLV, you will be able to appreciate. So PSLV is this much big. So he will not be even up to the height of the nozzle. Okay, now I have shown you a cross section of the PSLV. You see anything now from the limited discussion what we had, you know, I think you will be able to identify what kind of stage is this. It's a solid propulsion stage, right? Because you see the rockets. This is a liquid propulsion. You can see both tanks. On top again you see solid propulsion. On again you see something. Why all these stages? Why can't you use a single stage? Another question naturally. Huh? Yeah, one at a time. Yeah.
That is parts it space is lesser. One portion is getting fired and that part is gone.
Understood. That is you are basically telling. But I can say the other way. No, I have only one part and I throw it at the end. Cost is cheaper. You know, when you have only one stage, it's cheaper.
It's less efficient.
Huh?
Less efficient. Less efficient.
Surface tension.
Less efficient.
Yes, less efficient. Less efficient again is a very subjective word, right? So,
So since the solid propellant has more power, it can basically go against the gravity, which will be higher in the surface of the earth and lower in the heights.
yeah.
So
It's a very good answer. Let me just interrupt. It's a very good answer, but it only tells you why solid engine is selected. Why different stages are there is not the answer.
after that we don't need the.
No, I understood. Your answer is basically why first stage solid, why second stage liquid. You still don't address the question why there is stages in the first place. Yeah.
Because we can stop the liquefied engine.
Again, the same answer to what I told him.
Because we come across different phases.
Yeah, now because of lack of time, now I'll just see. Suppose if the same question I have thrown to you, and if you discuss among yourself, I am sure within 5 to 10 minutes you yourself will come out with an answer. Now someone will make one part of it, someone will find a problem. This is what you call discussion. There is a fundamental elements in physics and philosophy. This is what thesis, antithesis, and together synthesis. That's how philosophy evolves. And all the physicists are basically called natural philosophers once upon a time because they were basically philosophers. They used to think. They never used mathematics. Mathematics came later. So you have to have a thesis. Someone will question that thesis. That is what we call an antithesis. Then the thesis and antithesis, they will discuss and they will evolve a common form called a synthesis. That's how philosophy has been evolved, right? So now again come back to this. Whatever you said are all right. But the specific question what I asked was, why you want different stages? You should understand why you want a rocket in the first place. The rocket is required to put something in the orbit, right? The rocket is required to put something in the orbit. Okay, Dr. Shanid will explain to you. What is these numbers. Okay, if you want to put something in an orbit around 300 kilometers, the rocket should have a velocity, or rocket should give the velocity to satellite something like 8 kilometers per second, 7.8 to 8 kilometers per second. Am I right? 8 kilometers it has to give. So what the launch vehicle has to give to the satellite? A velocity of the order of 8 kilometers per second. Now, how will you get velocity? Only when you accelerate. Am I right? Only when you accelerate you will get velocity. Fundamental principle, right? Velocity you will not get by sitting together. If you are standing on the earth, you will have zero velocity. If you accelerate, you increase velocity. So to accelerate, how a rocket accelerates? By force. But the thrust of a rocket does not increase. The rockets don't have an accelerator. The thrust of the rocket is same. So how a rocket can accelerate? So what is the law? F is equal to m into a. If you want better acceleration, you want less mass. How you give less mass? By throwing out unnecessary things. Okay, in a simple way, there are mathematics things involved, we will discuss if time permits. The fundamental principle is, unless you throw away something, as and when its application is over, what he said, it's not efficient. I am only giving an explanation of what he said. It's not efficient to have a single stage, because when you are having a single stage, at the end of the rocket, you imagine a big tank, a small quantity of propellant, unnecessary, inefficient. It is something like traveling. When you travel, who has come from the farthest place here? Someone maybe from Maharashtra, no? Who has come from Maharashtra? Very good. You both have come from where? Maybe Mumbai. Fine. So when you came from Mumbai, earlier, long back, people had only one choice. They used to have a big bottle of water, etc. Now, have you brought a bottle of a huge quantity of water in a Syntax tank from Bombay to Trivandrum? It has not even occurred to you, right? Because you know that you can always get water on the way. Even if I am telling you there is no water on the way, what you will do? You won't buy a tank. You may buy 5-ton bottles of small quantities of water, and as and when you complete one bottle of water, you will dispense with, right? You will never carry a tank. Why? Because it is inefficient. When you reach Trivandrum, you will end up with a huge tank with a drop of water. It's inefficient. You have to still carry the tank, right? Exactly the same principle is used for rockets, because as you said, it is inefficient to have a single stage, so use multiple. The mathematics we will discuss later. Now what I am trying to say is that's the reason why we have multiple stages in a rocket. Each and every stage adds its own velocity. If you want 8 km per second, the first stage may give 2 km, etc., etc. Now we will see the Shani does not come.
Yeah, it always comes.
Ah, okay. Yeah. How many more time? How much?
Actually 10 minutes.
10 minutes. Okay, good, sufficient. So if you take a particular vehicle like PSLV, no, the first stage is like this. The cross section details and all are there is something. It's, again I told you, you will having a lot of propellants here. There will be this system. Now this is the second stage, which is having its own system. One more physical principle I will just explain. See, when you are traveling in an air through an automobile, you have a steering. The steering will change the angle of the front wheels, and because of that you will be getting redirected. But here there is no steering, and even if there is steering, there is no purpose. You cannot have aerodynamic surfaces because there is no air. So what you do here is you call what you call the thrust vectoring. You change the thrust is a force and force is a vector, right? So that means a force is having both direction and magnitude. The moment you change the magnitude, the moment you change the direction, the force will change, the direction of the force will change. So in these cases, what you do is, hello Sunil, hello doctor. So what you do is, you can change the direction of the thrust by changing the direction. You see this? See, the nozzle is changing, no? So what you are basically doing, the vector of the thrust you are changing. Okay, magnitude you are not changing, but since force being a vector, even if you change the direction, you have a different force. So what I am doing here is I am changing the direction of the nozzle or direction of the thrust as a vector. So naturally, what name should I give in a physical term? It's called thrust vectoring. Very simple to understand. The direction is changed. So when I change the direction of this rocket thrust, the rocket will move in different directions as you want. Understood? So this is how it is done. Very simple, no? If you go by the principle, very simple, right? Fine. Now we will see the various systems and we will see a mission. Now I have around 10 minutes, I will take less than that. Now just imagine PSLV is there in the launch pad. Okay. So PSLV is there in the, this launch pad itself you may be seeing when you go to Shar. It's a big launch pad. PSLV itself is around 44 meters tall. It weighs around 300 tons. And then when it is in the launch pad, this is the next question. What is the velocity of PSLV? 0. Sure? 0. What is the altitude of PSLV? Surface. If I take, now another important point again, there is, you have to always mention with respect to the frames of reference. What is your speed now? 0. Okay, but Earth is spinning. So with respect to something else, your speed is different, right? So here also there are a lot of such complications are there. We won't go into that. For the time being, let us assume that PSLV is on the launch pad at 0 velocity, 0 altitude. Ultimately, what you want a velocity of 8 kilometers per second, and you want an altitude of say 300, 400 kilometers. So this is what you want, right? So the PSLV is in the launch pad. Now, as someone has mentioned, you require maximum force for liftoff. So I am lifting off the PSLV. So along with the main engine, lot of small engines are also there. So now the PSLV has lifted off. Okay, you see all the engines are firing. So at the point of beginning, the time was 0, the altitude was practically 0, altitude was, you can say 0. Now, after some time, the small rockets will complete its propellant. So what we should do, just like what we have done in the case of that water bottle, we will just dispense it off, right? So when there is a reduction of mass, its acceleration will go up. Not just this, each and every second propellants are getting consumed, right? Each and every second propellants are getting consumed and thrown out as gases. So the weight of the rocket is coming down, but the force is same. So when the weight comes down, when the force is same, what will happen? It will accelerate. So it will keep on adding velocities. This we call delta V. Okay, delta V. We will keep on adding delta V into the system. Then after some time, what will happen? The two airlet strap-on will also complete its function. It is getting separated. Now, first stage itself will complete its function. Now in physics, there is no value for sentiments, right? Because this rocket has taken you to this altitude. Hey, why can't we take it to orbit? No, he has come all the way. That kind of thing won't work in physics, right? That's why some of the physicists are very tough people, because they deal with principles like this. Okay, now you separate this. Now one interesting point, let me just tell you, the altitude at the separation is, the time is only 2 minutes. After hardly 2 minutes, the first stage has completed its duty and separated. Altitude is around 6.68 kilometer. The velocity is around 2 kilometers. Out of 8 kilometers, you have reached only 2 kilometers. But PSL, what happened to PSLV? There is a movie called Honey, I Shrunk the Kids. You know, have you seen? So the PSLV has got shrunk. Why? The entire mass of the first stage weighs around 140 tons. Each strap on weighs around 60 tons. Sorry, 12 tons. So 12 into 6, again how much? 77, 84. I mean, around 200 tons of PSLV has already gone. Out of 323 tons, 200 tons, of more than 60 to 75% of mass of PSLV is already gone. Why? As someone has asked me, you require maximum energy to lift it up, you require maximum energy to push it up through the atmosphere. Now, once it reaches the higher atmosphere, I will take hardly 2 minutes, there is something called heat shield that will be separated. Okay, again, what is the physics behind this? Because when you travel through the atmosphere, because of friction, there will be tremendous amount of heating. Okay, aerodynamic heating. So satellite has to be protected. So it is kept in a heat shield, but once you reach around 120 kilometer, hardly there is any air. So what you will do? The same principle of insensitivity. What is that? Dispense it. However helpful it was, you dispense it, because it's only a dead mass, nothing else. Once it reaches 120 kilometers, you just throw the heat shield, right? So again, second stage gets dispensed. Okay, and then third stage takes over and it goes in the orbit, and after some time, now the third stage is getting dispensed and you reach the orbit. Okay, so now here you can see, when you move it, now the rocket is slowly changing its direction. Okay, because the rocket lifts off like this, but ultimately the satellite is revolving like this. So the rocket will do all this. This is what yesterday beginning someone was telling, this is what you call the navigation, control and guidance of the system. And then finally, once you reach the altitude, the right altitude and the right velocity, you do cut off the engine from its function. Okay, PS4 will be cut off and then the satellite will be separated. So this is what you call a closed loop guidance. You continuously monitor the performance of the system and then you do this. So it has reached the orbit. Okay, so this is what a PSLV rocket basically does. What it does, it takes a satellite from the ground to orbit, and for that PSLV, if we compare with a human being, it has got its own sensors, it has got its own brain called an onboard computer, it has got its own limbs, what you call actuators. So it continuously senses its position data. You are asking, Sarir sir, you are asking how it finds out. There is something called inertial navigation, as sir has mentioned. So it will find out where its position is, it will navigate and it will give it to the ground called a telemetry system and it will go. Okay, so I think I have just taken my time and now we have reached orbit. So what is the fundamentals of satellites? What is the physics behind satellite? You don't know, naturally. You don't have to. Why? Because for that we have very eminent scientists here. So with this I wind up. Thank you.